Okay, hello everybody. This is part 2 of the Higher Physics 2019 written paper walkthrough. And in part 2 we're going to have a look at questions 7 to 11, which is on the particles and waves content of the Higher Physics course. Remember, the exam is 2 hours and 15 minutes long. That's a long slog, so we've split this over 3 videos, and this is the second in the series. There's your data sheet. And we're going to start where we left off last time, which is with question 7, and that is on the standard model of particle physics. Here we go then. Scientists have recently discovered a type of particle called a pentaquark, and pentaquarks are very short-lived and contain 5 quarks. And a lambda B pentaquark contains the following quarks: 2 up, 1 down, 1 charm, and 1 anti-charm quark. And we are asked for part A. Quarks and leptons are fundamental particles. Explain what's meant by the term fundamental particle. And I'm going with there, a fundamental particle cannot be broken down into anything smaller. That's for part 1. Part 2, state the name given to the group of matter particles that contain quarks and leptons. Well, they're fermions, and there are 12 of them. Part B, the table contains information about the charge on the quarks that make up the lambda B pentaquark. And there's our up-down charm and anti-charm quarks and the charges that's on them. And we have to determine the total charge on the lambda B pentaquark. Now remember, if we scroll up there, we're told that the lambda B pentaquark contains 2 up, 1 down, 1 charm, and 1 anti-charm quark. So let's jot that down in the table. There's 2 ups, 1 down, 1 charm, 1 anti-charm. And then we just have to add all those charges together to get the total charge. Now they're all expressed as fractions of the charge on the electron, so make sure you include the E when you're adding all these charges together. So we've got plus 2/3 E plus another plus 2/3 E. That's our 2 up quarks, plus minus 1/3 E is the down quark, plus another plus 2/3 E is the charm, plus minus 2/3 E is the anti-charm. And then all of them added together, 2 plus 2 is 4, minus 1 is 3, plus 2 is 5, minus 2 is 3/3E, which is plus 1E. So the charge on a pentaquark would be equivalent to the charge on a proton. Interesting stuff. Now let's move on then. 7 part C. One theory to explain the structure of the lambda B pentaquark suggests that 3 of the quarks group together and 1 quark and the antiquark group together within the pentaquark. And there's a wee diagram showing you that. And part 1 asks us to state the type of particle that is made of a quark-antiquark pair. Well, that'll be a meson. And part 2, the mean lifetime of another quark-antiquark pair is 8 times 10 to the minus 21 seconds in its own frame of reference. And during an experiment, the quark-antiquark pair is travelling with a velocity of 0.91 c, that's 0.91 times the speed of light, relative to a stationary observer. And we have to calculate the mean lifetime of this quark-antiquark pair relative to a stationary observer. This is a time dilation or a special relativity question. So let's go to our relationship sheet and write down the time dilation relationship. Now it's T dash that we're looking for here because it's the lifetime of the moving quark-antiquark pair relative to the stationary observer. So there's no rearranging to do here. It should hopefully just be a straightforward substitution of the numbers into that relationship. So there's the lifetime, and that's over 1 minus 0.91 c over c all squared. The trick here is that the 2 c's cancel out, and we're left with 1 minus 0.91 squared on the bottom. So if you do that on your calculator, you end up with an answer. It should be a longer time than the 8 times 10 to the minus 21, and we get an answer of 1.9 times 10 to the minus 20, or 19 times 10 to the minus 21 seconds if you prefer. So straightforward, 3 marks there, relationship, substitution and answer. Question 7D. The lambda pentaquark has a mass energy equivalence of 4,450 MeV. That stands for mega electron volts. Now you might not be too familiar with the electron volt as a unit of energy, but it tells us that 1 eV is equal to 1.6 times 10 to the minus 19 joules. And we've to determine the energy in joules of the lambda b pentaquark. So all we have to do is take the 4,450 mega electron volts, so don't forget the times 10 to the power of 6, and multiply that by 1.6 times 10 to the minus 19, and that will give us the energy in joules. It's a tiny wee number, 7.12 times 10 to the minus 10 joules. And then we have to calculate the mass of the lambda b pentaquark. Well, mass and energy can be made equivalent by using the relationship E equals mc squared, where the speed of light squared is the conversion factor between the two of them. So if we want the mass, m equals E over c squared, we want our energy in joules, so that's the 7.12 times 10 to the minus 10, and we divide that by 3 times 10 to the power of 8, don't forget to square it. And you do that on your calculator, you'll get a very, very small mass. It's 7.91 times 10 to the minus 27 kilograms. Right, hopefully that's the end of the standard model stuff. Let's move on to question 8. This is nuclear reactions. The sun emits energy at an average rate of 4.1 times 10 to the 26 joules per second. And this energy is produced by nuclear reactions taking place inside the sun. The following statement shows one reaction that takes place in the sun, and it's 2 heavy hydrogen nuclei that are fusing together to form a light helium nucleus plus a neutron, and that type of nuclear reaction is a nuclear fusion reaction. So state the name given to this type of nuclear reaction. It's nuclear fusion, and what's your spelling there? Part B, the mass of the particles involved in this reaction are shown in the table, and we've to determine the energy released in this reaction. So each of those individual particles is shown there with its mass, and so we have to work out the total mass before the reaction and the total mass after the reaction. And remember that mass is lost during this reaction and changed into energy, so we need to work out the lost mass. So let's work out the total mass before the reaction. That's the 2 hydrogen nuclei added together. That's 2 times 3.3436 times 10 to the minus 27 gives us 6.6872 times 10 to the minus 27. Don't round anything here. And then the total mass after the reaction will be the helium nucleus plus the neutron. So that's the 5.0082 times 10 to the minus 27 plus 1.6749. Always double check your arithmetic here, dead easy to mess this up. And there's our total afterwards, which should be less than it was before. Then to find the lost mass, it's just the mass before minus the mass afterwards, and that gives us 0.0041, or 4.1 times 10 to the minus 30 kilograms. That's the lost mass. And then if we want the energy produced, we use our relationship E equals mc squared, where m is the lost mass and c is the speed of light squared. So 4.1 times 10 to the minus 30 times 3 times 10 to the 8 squared gives us the energy produced from one of those reactions, 3.7 times 10 to the minus 13 joules. It's a very small amount of energy, that's because it's one reaction. Then we have to determine the number of these reactions that would be required per second to produce the sun's average energy output. Well, we were told the sun's average energy output if you scroll back a wee bit in the question, it was, there it's there, 4.1 times 10 to the 26 joules per second. Sometimes you've got to scroll back a page to find the information you need, so let's pop that in there. And the energy we got from one reaction, we've just calculated that in the previous part of the question. That was 3.7 times 10 to the minus 13 joules. So the number of reactions we need will be the energy output divided by the energy we get from one fusion reaction. So 4.1 times 10 to 26 divided by 3.7 times 10 to minus 13 is 1.1 times 10 to the 39 reactions every second. And that's what's going on in the sun. Okay, question 9. This is energy levels. A laser emits light when electrons are stimulated to fall from a high energy level to a lower energy level, and the diagram shows some of the energy levels involved. And in one particular laser, a photon is produced by the electron transition from E5 to E3 as shown. And just watch your powers of 10 here, because these are usually quoted as times 10 to the minus 19, but in this case it's times 10 to minus 18 joules. Anyway, part 1 asks us to determine the wavelength of the photon emitted, and it's a 4-mark question. That means there's a little bit of extra work to do here. So first things first, we can write down the relationship to find the frequency of the emitted photon based on the difference between the two energy levels. And on your relationship sheet is E2 minus E1 equals HF. But I'm going to write E5 minus E3 because those are the two energy levels that we're interested in. So it's going to be the difference between E5 minus E3, and that will be equal to Planck's constant times the frequency of the emitted photon. Now, because we are interested in the wavelength, then remember F equals V over lambda, or C over lambda in this case because it's the speed of light that we're using. So I'm going to substitute in C over lambda for F in that relationship. So let's put the numbers in. 2976. Should you double check these? So minus 2.976 times 10 to the minus 18 minus 3.290 times 10 to the minus 18. That's the two energy levels. And then Planck's constant, 6.63 times 10 to the minus 34 is on your data sheet, times, now I'm going to put C over lambda here. So speed of light, 3 times 10 to the 8 over lambda, and it's lambda we're interested in. The left-hand side on your calculator there gives you an answer of positive 0.314 times 10 to the minus 18. And then the 6.63 times 10 to the minus 34 times the speed of light is 1.989 times 10 to the minus 25. And remember, I'm not rounding anything. Don't round anything until you get to the very end. Rearranging for lambda and doing that on your calculator gives you an answer of 6.33 times 10 to the minus 7 meters. And that's 633 nanometers. Now, of course, you could have done it in 2 steps. You could have worked out the frequency first. But if you do that, don't round it. Leave it in your calculator before substituting it into V equals F times lambda. Right, moving on. 9, part A continued. This is part 2. The laser beam is shone onto a screen. The beam produces a spot of diameter 8 times 10 to the minus 4 meters. And the irradiance of the spot on the screen is 9,950 watts per square metre. We have to determine the power of the laser beam. Straight to the relationship sheet, irradiance is power over area. If we want the power, then the area of that circle, well, the area of a circle is in your additional maths relationships at the back of your relationship sheet. The area of a circle is pi r squared, remember? So P equals I times A. The irradiance was 9950, and the area of your spot is pi r squared. Now, careful here because we're given the diameter of the spot. So the radius will be half of that. That's 4 times 10 to the minus 4 metres. And we substitute that into the area of the circle. So pi times 4 times 10 to the minus 4. Don't forget to square it. It's just the radius that's squared. And then doing that on your calculator, we get a power of 5 times 10 to the minus 3 watts. 5 milliwatts. Nice question. Nice and realistic numbers there. Okay, what's your significant figures here? All the numbers in the question are 3 significant figures. So I'd be tempted to give my answer to 3 significant figures, 5.00. Don't forget, you'll not be penalised though if you go to 2 too many or 1 too few. Okay, let's look at part B. A student investigates how irradiance varies with distance d from a point source of light using the apparatus shown. And we have to describe how this apparatus could be used to verify the inverse square law for a point source of light. So we've got a small torch bulb or a small lamp, light sensor connected to a light meter and a meter stick. So the measurements we're going to make here is we're going to be measuring the irradiance on the light meter at various distances, which we're measuring with a meter stick, and we're going to determine I times d squared for each set of readings, and I times d squared should be equal to a constant, and if it is, then we have verified that I varies with 1 over d squared. That's the inverse square law. Irradiance varies with 1 over the distance squared. Question 10. A student carries out an experiment to investigate the effect of a grating on beams of light from 3 different lasers. And there's your typical diagram of a laser shining through a grating and producing an interference pattern on a screen, although we're only seeing the central maximum and the first order maximum, the first dot out from the middle. Now the 3 different lasers produce red, green and blue light respectively. Each laser beam is directed in turn towards the grating, and the grating has a slit separation of 3.3 times 10 to minus 6 metres. Remember that's small d in your grating equation. Now part A, state which of these 3 colours of laser light would produce the smallest angle theta between the central maximum and the first order maximum. And you have to justify your answer. So let's go to our relationship sheet again and write down the grating equation m lambda equals d sine theta. Now, there are 3 colours, red, green and blue. You should know the approximate wavelengths for each of them. So for red it's 700 nanometers, green is about 500 and blue is about 400 nanometers. Now the way that I remember that is that blues get 4 letters, 400, greens get 5 letters, 500, and red's the same as scarlet. Scarlet's get 7 letters. You could of course also look up the data sheet to get an idea of the wavelengths of specific colours from their spectral lines. Now we have to state which of these 3 colours would produce the smallest angle. So if we look at the relationship, if the wavelength is smaller, then the angle will be smaller. Now this is assuming that m, that's the order of the fringe, and d, the slit separation, are constant. And because blue laser light has got the shortest wavelength, it will produce the smallest angle. 3 marks there. That's pretty tricky. 1 for making the connection between the wavelength and the angle, 1 for saying that m and d are constant, and 1 for saying it's the blue laser that produces the smallest angle. Okay, on we go. Question 10, part B. The angle theta between the central maximum and the first order maximum for light from one of the lasers is 8.9 degrees. We have to calculate the wavelength of this light. So there's our grating equation again. M lambda is d sine theta. It's the first order maximum, so m is 1. Remember our d was 3.3 times 10 to the minus 6. So let's pop that in there to remind us. And it's the wavelength that we're looking for. Our theta is 8.9 degrees. So no rearranging required here. Lambda will be equal to 3.3 times 10 to the minus 6 times the sine of 8.9 degrees. And if you do that in your calculator, you get an answer of 5.1 times 10 to the minus 7 metres. Always useful to convert that into nanometres. That's 510 nanometres, because we need that for part 2. It says determine the colour of the light from this laser. Well, 500 nanometres is green. You could, as I say, always check that on your data sheet. There's your data sheet there that gives you approximate wavelengths of red, green and blue. If we look at the cadmium, the element cadmium, its wavelengths there for red, green and blue, then the green is 509 nanometres. So that should give you an idea that if we've got an answer of 510 nanometres, then it's going to be green. Part 3, another student suggests that a more accurate value for the wavelength of this laser light can be found if a grating with a slit separation of 5 times 10 to the minus 6 metres is used. Well, that's a bigger slit separation than we used previously. We used 3.3 times 10 to the minus 6 earlier on in the question. So if D is greater, then your maxima, that's the dots in the interference pattern, they'll be closer together, and that will make theta harder to measure. And if the angle is harder to measure, then your angle measurement is going to have a greater percentage uncertainty in it. That's pretty tricky. Let's have another wee look at that relationship again. So, if m is constant and the wavelength doesn't change, so if m is the same and the wavelength is the same, then if d is greater, if your slit separation is bigger, then your angle has to be smaller. And that'll be harder to measure. That's really tricky. 2 marks. Okay, last one for this video. Question 11. Diamonds sparkle because light that enters the diamond is reflected back to an observer. This is refraction and critical angle. So part A. A ray of monochromatic light is incident on a diamond at an angle of 49 degrees. The refractive index of diamond for this light is 2.42, and we have to calculate the angle of refraction, theta. It's a calculate question, so we go straight to our relationship sheet and write down the refraction relationship. N equals sine of the angle in air over the sine of the angle in glass. We know the angle in air is 49, and we know the refractive index is 2.42, and it's sine theta 2 we're looking for. That's the angle in the diamond. Now the advice is to substitute the numbers in first, so 2.42 equals sine 49 over sine theta 2. That will guarantee you the first 2 marks, and then rearrange it for sine theta 2. So it's sine 49 over 2.42, and then so theta 2 is equal to 18.2 degrees. That's the angle in the diamond. Part B, calculate the critical angle of the diamond for this light. Remember, critical angle is the angle in the diamond at which the refracted light in air has reached 90 degrees, so it can no longer be refracted, and at angles above that it'll be totally internally reflected. There's a relationship for working out the critical angle, and it is. It's the sine of the critical angle is equal to 1 over the refractive index. And for this diamond, that'll be 1 over 2.42. And if you do that in your calculator, then theta c works out to be 24.4 degrees. That's the critical angle for the diamond. So any light that is in the diamond at angles greater than that is going to get totally internally reflected. So 11 part C, moissanite is a transparent material with a greater refractive index than diamond, and a sample of moissanite is made into the same shape as the diamond. State whether the sample of a moissanite sparkles more or less than the diamond, and you must justify your answer. And remember, in a must justify question, then you can't get the first mark unless you have a justification to support it. So, moissanite will sparkle more than the diamond will. Why is that? Well, it's got a greater refractive index, so its critical angle will be smaller than diamond, and therefore more light will be totally internally reflected back towards the observer. And you could of course also support your justification there with a calculation using a larger refractive index. Question 12 is electricity, and we will save that for the next video where we'll cover internal resistance, capacitance and semiconductors. We'll see you in part 3. See you in the next one.